Hello, we are representing Road Asset Consultants, who are an experienced company that offers an end-to-end asset management service from data collection to treatment prioritisation. The team of engineers that were involved with the project are Daniel Goodwin, Josh Moran, Abdul Karim Mukhtar, Jason Bowen and Peter Coleman.
The brief was set out from the client. He also tasked us to assess the maintenance requirements of the Boston University campus road network using the provided key asset highways pavement management system.
The key objectives agreed with the client were to submit a prioritized maintenance works reflective of the current conditions, to define a maintenance standard that reflects the prestige of the university network and the impression that the client seeks to impart on the students and visitors.
Following a desktop study of the university's road assets, we considered the most important section of the network to be the ring road due to the traffic type's volume and significance in comparison to the other subsidiary roads. Having defined the extent of the network, a methodology was then created and adopted.
The first task in the methodology was to survey the network and obtain the condition data. We then identified appropriate treatment types for the nature of the road in relation to the defects that we found. We defined intervention levels for each of the treatment types. We then imported the condition data and the intervention levels into the pavement management system. We then ran the analysis to generate a prioritised list of works, and then we manually formulated a programme of these works.
In terms of the condition data, we have defined 4 key areas to present, which include the inventory referencing system, the types of defects to be surveyed, the methods of collection, and the defect characteristics. The brief from the client stated that the University Ring Road would be the primary focus for the condition survey. From the outset, we had to create an inventory that would enable us to divide the site up logically. The road reference that we decided upon was RR, which represented the ring road. Within our desk study, we estimated the distance of the ring road circulatory to be approximately 1,300 metres. This was calculated using AutoCAD's Ordnance Survey data. This allowed us to break up the site into 3 logical areas, which could be given a unique section reference, which started at 001. Each section was then further broken up into subsections of 50 metre intervals and given references starting at 01. The next stage was to determine what defect types were to be collected. The primary data required from the survey was roughness, which was to be measured mechanically using a Merlin instrument. This was then also done in conjunction with visual surveys that picked up the location and severity of defects such as potholes, cracking and rutting, as well as doing a basic traffic survey. The Merlin equipment is an acronym for a machine for evaluating roughness using low-cost instrumentation. The roughness of a road surface is an important measure of current condition and a key factor in determining vehicle operating costs on poor quality surfaces. As a group, we spent time familiarising ourselves with the Merlin instrument, calibrating it as per the user manual, and undertaking a practice run before carrying out the real survey. We worked as a team when surveying the campus, whereby one person would move the Merlin equipment whilst another would record the readings on the chart. Another person would then record the visual survey defects and traffic counts, with another operating the measuring wheel so we could relate the defect to a location on the campus circulatory. The 5th person would then be a lookout for the whole team, while making sure the survey signs were moved up as the survey progressed. Roughness was measured in the wheel tracks of the road, and at each rotation of the wheel on the Merlin machine, a reading of roughness was measured, and then repeated for the entire length of the ring road. To assist in the recording of the defects through a visual survey, we created a schematic survey plan which was broken up into an inventory referencing system. We then used a key comprising of hatches and line types which indicated the various defects, which enabled the survey team to quickly and accurately record location and types of defect. To help determine what governed each type of defect, we came up with a standard representation and description that referred to the type of defect. The first example is of alligator cracking. This defect may have been caused by excessive loading, weak structure, or poor drainage. Here is a typical sample of block cracking. This defect is characteristically aggravated by low traffic volumes. This is a representation of ravelling, where the cause of the failing could be down to poor quality mix, where the asphalt binder has been hardened excessively. High traffic volumes or poor drainage are other issues. Longitudinal and transverse cracking look like this. This defect could be due to poor construction joints, shrinkage of the asphalt, fluctuating temperatures, or cracks in the substructure. This is an example of a pothole. The deterioration of potholes are typically accelerated by traffic volume. They are generally caused by stress through water freezing, which breaks out the pavement, but can also be due to a poor surface mixture and weak spots in the subgrade. This is a sample of rutting, where the problem stems from insufficient design pavement thickness, lack of compaction, and lateral movement of the pavement layer through high traffic volumes. And finally, an example of depression points, which is usually due to settlement or failure in low pavement layers through poor construction techniques.
We've defined 6 treatment options that are appropriate for the university road network. These are patching, crack sealing, surface dressing, inlay, full reconstruction and replacement of block pavers. We have addressed localised pothole defects with the patching treatment. The treatment is intended to remedy small areas of failed carriageway and restore the surface regularity. The process involves excavation of the pothole to sound material at the edges and the base. The base and edges are then sprayed with a tack coat. Bituminous material is laid and compacted with a plate compactor. The cost of this treatment is approximately £50 per square metre. In locations where long lengths of non-structural cracking and joint failures are present that don't cover a large surface area, we have specified a crack sealing treatment to prevent water ingress and improve skid resistance. This form of treatment, also known as overbanding, costs approximately £5 per linear metre. In sections where there are large areas of non-structural surface cracking, it isn't practical to apply a crack sealing treatment. Therefore, in these locations we have specified a surface dressing treatment. This is a process of waterproofing the pavement by sealing the surface with a layer of bitumen emulsion and aggregate chippings. Surface dressing is intended to lengthen the predicted life of a pavement that's showing minor non-structural cracking. The thin layer of bitumen emulsion is impermeable and prevents water ingress, and the chippings improve the surface texture and skid resistance of the road. The treatment is the cheapest of all the treatments suggested at £4 per metre squared and is relatively fast. Up to 5,000 square metres can be treated in a working day. In areas where the carriageway surface is deteriorated beyond a surface dressing treatment, but doesn't exhibit characteristics of a deep structural failure, we have specified an inlay treatment. This treatment involves the replacement of the top 100mm depth of the pavement. The first stage of the process is to mill the existing carriageway with a planer, then lay a 60mm depth bituminous binder course, followed by a 40mm depth surface course. The cost of this treatment is approximately £30 per metre squared. The most expensive treatment option is a full reconstruction of the carriageway that will cost in the region of £90 per square metre. This process will involve the excavation of the full depth of the pavement's bituminous layers, that in this case is assumed to be approximately 300mm for the ring road, and replaced with new material. This treatment is the most disruptive to the network and will require lengthy closure of the ring road. However, reconstruction will be the most effective in extending the life of the pavement. The final treatment type is the replacement of block pavers to address the defects that are apparent in the short lengths of shared space surfacing. The defective blocks will be removed and replaced with new blocks on a sand bed that are supplied by the same manufacturer.
My name is Mukhtar Abdul Karim. I am going to present to you the intervention levels used in this project. Before getting to the details, first, what is intervention level? Intervention level is the threshold above or below which action must be taken to ensure that standards are met, often expressed in terms of defined threshold of road condition, response time, or performance. The picture on your screen gives you an example of what intervention level is. It is an example of a road that undergoes cracking until it reaches a threshold level set by the organization and treatment is done, such as crack sealing, overlay, and others. Standards were checked for the intervention levels. Based on the guidance of road classification and primary route network, the road investigated ring road is classified as unpractified road, which have low intervention levels. Although the team understands the importance of ring road in the mobility and accessibility on campus. Therefore, the intervention level used are based on this level of importance to the university needs, thus making the intervention level higher than the ones provided in the standards. On the screen, you have been provided with a table showing the intervention groups and the different trigger levels for each defect coupled with the treatment types. The intervention levels are grouped into two groups. Group 1 deals with bituminous surface, while Group 2 deals with the block paved surface of the carriageway investigated. I am now going to pick one of the defect group as an example. For Group 1 has a defect of surface cracking with a trigger level of less than 5%, which is the percentage of defect across the subsection investigated, and the treatment type coupled with this is crack sealing. This is just the agreement between me and my group members.
A prioritized list was generated for the network subsections which required treatment. This prioritized list consisted of the subsections whose level of defects ranged from the most severe at the top to those with minimal defects at the bottom. Before generating the list, the defects and the road condition data were initially input into the KAH software database. This is a first-generation decision support software tool used to assist in objectively developing a priority list with respect to road condition. A defect rating value for each subsection was developed using the level of condition of each subsection which required treatment. The defect rating is a function of the type of defect, the quantum of the defect, and the traffic group of the subsection. The prioritized list was generated in the Generate Priority List subtab under the Report tab of KAH. During the run, the subsections' defect ratings are compared to the intervention levels and groups. The preferences used with the intervention levels are critical so as to ensure that multiple interventions aren't included to solve the same defect on the subsection. For example, on a particular subsection, which may have enough cracking and roughness to trigger an inlay treatment, while at the same time, due to the level of cracking, crack sealing may also be triggered. Preferences from the intervention groups were used to ensure that the most appropriate treatment would be selected, and in this case, inlay was selected as it addressed both defects. A prioritized list shows the range of subsections from the highest defect ratings at the top to those with the lowest defect ratings at the bottom. The weighting placed on defects would also impact the defect rating, where some defects would be given greater priority than others given its importance. Cost was not significant in providing the prioritized list. As was seen in the listing, some items which may require a more costly treatment were lower in the list than some with lower cost. This occurred as a result of the emphasis placed on the defect rating, where the percentage of the defect was used. Thus, it was likely that the percentage defect and/or the type of defect on the subsection were higher than in lower placed subsections. For example, the subsections with priorities 8, 9, and 10 indicated a situation where cost was not the primary determinant. In fact, the treatment costs for the subsections at 8 and 10 are higher than that at 9, and clearly something else would have had to be the major determinant.
This would be the defect rating on the subsections, where that at 9, it was higher than that at 10, but lower than the rating for the subsection at 8.
The KH was used in evaluating the network and the effective pavement condition was found. The following treatments: crack sealing, patching, surface dressing, and inlay were found as the output, with total treatment amounting to 92,232 pounds. However, we are strongly recommending surface dressing for uniformity of the pavement surface after treatment. This will improve the functional capacity of the network and prevent ingress of water, hence prevent any possible initiation or acceleration of any structural damage in the road foundation. Moreover, we are also recommending that your administration should, in the future, request for our consortium to go further and perform for you a multi-year economic and engineering viability analysis of the various maintenance options for the different sections in the network using HDM4. This will enable you to know before implementation which maintenance project alternative will give you the best net present value and economic internal rate of return. This brings us to the end of our presentation. We wish to thank you for your attention and we'll be glad to answer any questions.